All right. Can people hear me back there? Are we good? All right. So last time we talked about a convex hull algorithm, Chan's algorithm. It runs in optimal time n log h, where h is the size of a convex hull. It combined, interestingly, two slower algorithms, Jarvis's March and Graham's Scan, into a faster algorithm, which is interesting. Any questions about any of that? This is what we did last time, the last half of the last time. So I want to talk about convex polygon intersection. To intersect two convex polygons, let's see. I think my other file was missing a couple of slides, so we'll go to the one from the website. Yeah, there we go. All right. To intersect two convex polygons and find out their intersection, if one exists, because an intersection may or may not exist, you can do it in linear time, it turns out. So to do that in linear time, we'll use the same method that we did for planar subdivision, the slab method with the trapezoids. We'll adapt it to do convex hull or convex polygon, more generally, intersection. So we sort the x and the y coordinates. We sort the two polygons by x coordinate. And that's easy to do in linear time because polygon is given to you in order around the periphery of the polygon, the points and the edges in order. So it goes increasing and then decreasing. So you can take the increasing and then the decreasing and merge the two lists, and you have all the x coordinates sorted in linear time because it's a polygon. And then you do this vertical slicing business, and you do it for both polygons. And so the scenario looks like this. We have a blue polygon, we have a green polygon. Create all these vertical slices, and then partition into these trapezoids. For every slice, you have these blue trapezoids for the blue polygon, and separately you have the green trapezoids for the green polygon. And you do that in every single vertical slice that goes through every point of both polygons, of either one or the other polygon. And then you go slice by slice, and you intersect a blue trapezoid in that slice with a potentially green trapezoid in that same slice, if one is there. Right? Some slices have only blue trapezoids in them, some have only green trapezoids in them, and some have both. So the ones that have both intersect the two. Intersecting two trapezoids can be done very quickly in constant time because there's only 4 edges per trapezoid. Some trapezoids are degenerate, they're even triangles, so it's even less than 4, it's 3 edges. So you can do these intersections slice by slice in linear time, in constant time per slice, to a total of linear time across all the slices. And then, once you have all these intersections in red, you stitch them left to right, one into the next, into the next. You basically go one at a time as you go to the next red intersected pair of trapezoids, you stitch that to the previous one, and you stitch the intersecting, you stitch the intersection of the two original polygons in this manner, one pair of trapezoids intersected with each other at a time in red as you go left to right. And basically that all happens in linear time, and so the total time to intersect two polygons that are convex is linear time total in the overall number of vertices across both polygons. How many get this approach? Okay, any questions about that? Okay, so it's important that you see that it's in linear time, that nothing here takes more than linear time. So this generalizes to higher dimensions. You can intersect three-dimensional polygons, which are called polytopes, or even higher dimensionals than three. And you can use this to intersect many convex polygons with each other to find the overall mutual intersection of all of them, not just a pair. It costs you a little bit more extra in time, but we'll see how that grows in a second. And this method also generalizes to unbounded polygons as long as they're convex. Unbounded means they go off to infinity in some direction, potentially, as opposed to be completely enclosed in a finite area. So let's see how the unbounded one works. Pretty much the same way, but let's just go through it. So now some of the polygons, one of the two polygons can be unbounded. So this green one here has no bound in this direction, right? The blue one is bound, but the green one goes all the way to infinity. The intersection is still well defined with a bounded one intersected with an unbounded one. The intersection obviously will be bounded because it's the area common to both. So the intersection is in red here of this green and this blue polygons like that. So how do we find that if some polygons are unbounded? Well, exactly the same way as a minute ago. You do all these vertical slices. The unbounded one yields more vertical slices, and some of those slices can go off and be unbounded also. So, the slices in green here, let me backtrack. There are the blue slices, trapezoids induced by the blue bounded polygon. And then next we'll have the green slices or trapezoids induced by the green unbounded polygon that's going off in that direction. And then you compute the intersections of the two in red, like we did in the previous slide. And once you do that, you stitch them across just like you did before, and you get the overall pairwise intersection of an unbounded with a bounded polygon. Notice that this trapezoid here, induced by the green unbounded polygon, is an unbounded trapezoid. How many can kind of visualize that? It's just going off in that direction. That's okay. It's still technically a trapezoid, if you will. It's just a degenerate one. Instead of degenerating to a triangle or to a point, it degenerates into a half plane or a big piece of the plane, actually, unbounded piece of the Euclidean plane. So this can be generalized to arbitrary numbers of polygons, convex polygons. So let's see how that works. And again, some of these polygons can be unbounded, others can be bounded. It doesn't matter. The same scenario still works. So how do we do K polygons? So here's 4 polygons, a yellow one, a green one, a purple one, and a blue one, and there's the intersection in red of all 4. Now again, keep in mind the intersection may not exist. There could be disjoint, or there could be pairwise disjoint. There could be pairwise intersecting, but all K of them may not intersect together all at once. So then the intersection doesn't exist. The intersection is not just pairwise or triple-wise, it's the intersection of all of them together. Okay, so that's the intersection there in red. So how do you compute that? And again, it's important that all these polygons be convex. Convexity is what makes this easy to compute. By easy, we mean linear time here. If the polygons were not convex, all bets would be off. It'd be much harder to compute intersections. So the idea is to do divide and conquer. Intersect the first half of the set of polygons together, and then intersect the other half of the polygons together, and then intersect the two intersections. Because the intersection operation is both commutative and associative. You can do it in any order you want, and you still get the same answer. It's like addition. right? You can add a bunch of numbers in any order you want, pairwise, triple-wise, or whatever, as long as you keep adding the partial sums. Eventually you get the same answer as the total sum. Same for the intersection. So you can do it half and half, and then intersect the two halves. So at every stage of this recursion, if you will, you're only intersecting a pair of polygons, and you're intersecting them just like you did on the previous couple of slides. So the total amount of work you're doing is easy to see that it converges pretty quickly. To intersect k polygons, first you intersect k over 2 together, and then k over 2 together, and in linear time you intersect the two intersections. So this is like merge sort, basically. This is like merge intersection, like merge sort. Same kind of structure to this algorithm. And at the very bottom, you're intersecting just pairwise. And so you're doing a linear amount of work at every level, and there's k polygons, right? So how many levels do you have in this kind of recursion, divide and conquer? If you have log of k. So the total amount of work you're doing is log k levels times linear per level, just like merge sort. And so the total amount of work is n times log k. Okay. And again, the bottom line, you know, of the recursion, the base of the recursion is just pairwise intersections. Total time n log k. Now it turns out that n log k is also necessary. That we didn't prove it here, and the proof is not trivial, so we're going to skip the proof. I'm just giving you the bottom line that omega n log k time is also necessary, lower bound, to intersect k convex polygons. So this algorithm is obviously optimal. So given this theorem, wait for it. There we go. Makes this algorithm optimal. This result that's also a lower bound. Any questions about this? So we're using pairwise intersections to do k-wise intersection, generalizing it. And they could be both bounded and unbounded. Any one of the polygons can either be bounded or unbounded. You can mix and match any combination of bounded and unbounded polygons. But they all have to be convex. Otherwise, this method doesn't work as it stands. You have to go to more complex methods to handle non-convex general polygons. Okay. Another interesting problem in computational geometry is the diameter of an object. The diameter is the pair of points of that object that are the farthest apart. So farthest apart pair of points. So you can do that with polygons, with point sets, with more complex objects. But what's the pair of points belonging to the object that are the farthest apart? So that's naturally called the diameter. It's how wide that object is at its widest point. Okay. So with convex polygons, it turns out you can do that very quickly. In general, it may take more work, but for convex polygons, it can happen quickly. Find the farthest pair of points. Now, if you didn't care about time or efficiency, what's a brute force method of doing this? Look at every pair, right? And then you'll know and measure the distance for every pair. How long will that take? Every pair. N squared. So obviously, it works. It's simple, but it's not efficient. It can do much better than n squared. And first, let's show a lower bound. Obviously, it's not going to happen quicker than linear time, because you have to look at every vertex. One way to see that it's not going to happen in linear time, in less than linear time, in sublinear time, is consider such an example where all the points are in a circle. So that the diameter of this point set will simply be any antipodal pair, any pair across the diameter. That's the diameter, but there's many other diameters. And they're all equal to each other in terms of diameters. And so that will be the answer. But if you didn't look at every point, if you somehow got the answer from a general algorithm that finds the diameter of a point set, or even a polygon, and you happen to not look at every point, one of the points that you didn't look at could have been right outside the circle. And then once you have a point outside the circle, the diameter is no longer this guy. It's this other distance that's longer. The red distance here is the new diameter, which is longer than this old diameter. It's farther away. How many can see that? And then that could have been the point that you didn't look at. And if that was the case, you couldn't have known that diameter is is the red, because you haven't looked at that point, you would assume it was this other diameter here that's shorter. So that's basically an argument that every point must be looked at. We made a similar argument for the minimum of n things, requiring to look at every single item, because if you didn't look at one of the numbers to find the minimum of n numbers, one of them could have been a googol or minus a googol, and you wouldn't have gotten the right answer if you didn't look at everything. So that's the obvious lower bound that's linear. So it turns out you could also have an algorithm that will solve it in upper bound linear, which makes the algorithm, linear time algorithm, optimal. Okay, so we already talked about the quadratic time if you look at all n choose 2 pairs, but you might do better if you do some sort of a binary search. For every point, look at the farthest point using some binary search. Because if you have a point here and you want to look at the farthest point from it, you don't have to look at every other point. What you can do, because they're sorted in polar order, in polar angle, what you can do is look at the points that are farther and farther away and hop in that list in a binary search kind of fashion to look at to find the farthest point away relative to that point. And there could be a couple of ones that are farthest away. Like this is the farthest in this direction. So the distance goes higher, higher, highest, and then lower, 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 because the green is smaller than the red in terms of total distance. And then it can increase again, but it's still not, it's not going to wildly change up and down and up and down. It's going to increase and possibly decrease and then increase again. And so you have this kind of twin peaks kind of phenomena. And you can imagine how you can do a binary search on these points in blue around the periphery of the blue polygon there to make sure that you find the farthest away in some sort of a binary search. So for every point you want to find the farthest away, and there's n points, and you can do a binary search. It's like logarithmic time per point, and it's kind of an n log n algorithm. Just so you don't think that quadratic is the only kind of naive way to do it. There's a slightly less naive way to do it that can be done in n log n. But we're still going for linear. So we're going for something that's even better than that. So here comes the linear time algorithm. But first, let's note that the diameter of a polygon, of a convex polygon, is the largest distance between any pair of points. And another way of characterizing the diameter is if you have a parallel pair of lines, or parallel to each other, that both are tangent, they're tangent to the polygon. Of all such parallel lines that touch the polygon on both ends, the diameter is the largest separation of any such pair. How many believe that? Okay, it's straightforward. It's not an axiom. It's a theorem. And you have to prove that. But it's not hard to prove that. And intuitively, it's pretty straightforward. So here's an example of a diameter. It's not the largest diameter, but the diameter is the largest distance between any such two tangents in red. Okay. There's a tool in engineering. It's called a calipers. Caliper is a tool that keeps a pair of planes parallel to each other as you vary the distance between them, and it's used to measure the width of irregularly shaped objects. How many have seen calipers or have seen it in movies? Okay, good. So, you can measure the width of a human head. You can measure the width of some oddly shaped object like an orange or a pear or whatever. And mechanics use this all the time when they work on engines and so on. So in a sense, we want to create like a computational caliper to measure the diameter of this object. Because if you take this caliper and you kind of rotate it around the object, if you have a caliper that's kind of spring-loaded but only goes up in terms of distance, not down, and you start rotating it around some object, and it can only expand but not contract, eventually when you finish a full rotation, that separation of the caliper will be the diameter of this object. How many get that? So that's kind of a mechanical analog of the algorithm we're about to see. And in fact, that's why we call the algorithm you're about to see the rotating calipers method. But it's a computational version of this mechanical analog that you can actually do in real world. All right, so find the horizontal max x, max y tangents. That's easy to do in linear time. Find the max x, the max y and the min y And that's the two red lines here, are the two tangents above and below the object, which is the polygon. And then start rotating it. So you rotate it until it hits the next point. And you always measure the distance between these two red lines every time you rotate it to the next point and to the next point. So literally, we're kind of rotating this pair of calipers in red here. Then rotate it some more until it hits the next point. The next point, by the way, could be either on one of the red lines or on the other of the red line. You're not sure which, but you look at both combinations, okay? And measure the distance between the red lines at this point also, which can be done in constant time for a pair of fixed lines. And then anchor the line at this next point, which was here, and rotate it one more time, like this, until it hits the next point, either on this red line or on the other red line. And keep doing this. How many can see what's going on here? Yeah, it's pretty straightforward. It's intuitive, right? It's the rotating calipers. And then you keep going. And you keep going. And look, the distance between the red lines, they're always parallel to each other. Varies depending on how thick or how thin the object is at that level of angle of rotation. But eventually, you'll know what the maximum angle was as you keep rotating it around. And until it hits an edge, the distance between the two lines remains constant. So you don't have to worry about what happens between the lines hitting the next edge or the next point or the next, because not much happens in between. So when I say rotating the calipers computationally, I don't mean continuously through every single infinite number of values of the real number, which is the angle, but only discretely to the next, to the next, to the next. So the calipers are not really computationally rotating smoothly like in reality. They're jumping to the next, to the next, to the next. I mean, how many understand that? So, the analogy breaks down a little bit there, becomes from continuous to discrete, and you really want it that way. Otherwise, it'll take forever to do literally forever to do the rotation. If you have to go every value in between, there's an infinite number of real numbers for the angles, right? But by the time you're done with this rotation, you'll know what the maximum separation was of these two red lines when you finish a full rotation. Do you have to do more than one rotation? No, because then you'll just get the same result over and over and over again. You've done one rotation and you know the entire set of possible separations, and that's it. And remember, these points are sorted by polar angle when you're given the convex polygon. And so you always know what the next point, when the next point, when the next point is in constant time as you're doing this rotation. So the entire algorithm, how fast does it run? Should be pretty clear at this point. Yeah, asymptotically. Big O of n, yeah, same as n, it's linear time. So in linear time, you'll finish this rotation. So in an animated kind of continuous way, it kind of looks like this. And these dotted lines here, are all the distances that we're measuring as these two pair of parallel calipers are rotating around in every possible way. Any questions about any of this? Pretty intuitive, right? And it's pretty clear that it's linear time. And this method actually does more than finds a diameter. It finds every antipodal pair of points. Antipodal means every point is counterpoint if you put a tangent at that point and wherever other point a tangent to the polygon. So it finds not just the diameter, but every antipodal pair of opposite points on both ends of the object as you touch two parallel planes to it from both directions. So it does actually more than just the diameter. The diameter is just one of those antipodal pairs, but it finds all of them. So it does extra work for you. It's still in linear time. So it's doing some heavy lifting that you don't even utilize for just diameter, but sometimes you want all antipodal pairs, and that gives it to you also. It has a lot of applications, this algorithm. Questions so far? Okay. So here's a paper that's written just on this method of the rotating calipers, and the author takes you through about a dozen different applications of this technique. One of them is to find the diameter, which we just did. But this technique of rotating caliper is so powerful and so intuitive, so efficient, that it could be used to solve dozens of other problems. So let me just show you a few, just for good measure. See how much mileage you're getting out of this simple technique. So we already talked about the width or the diameter of a convex polygon. That's like application number one. But there's dozens of others. You can also find the minimum area enclosing rectangle. So you can rotate two parallel planes and two orthogonal planes, so that's always a rectangle, and you keep rotating it, and keep track of the area of this rectangle as you rotate it, and it only changes at discrete values, which are the vertices of this convex polygon. And at the end, you'll find the smallest enclosing rectangle. By smallest enclosing rectangle, we mean the rectangle with the least area that completely surrounds the original polygon, that contains the original polygon. And often you need to, you want to do that. So this linear time will get you that too. How many can see how that would work, the rectangle? So instead of just one pair of lines, have the pair and the other pair, all four of them tangent at right angles to each other. And as you rotate this rectangle around, it'll change its width and height, but you'll keep track of the area at any moment of change, which is when the next vertex is hit, when the next vertex is hit. And eventually you'll know what the minimum rectangle in terms of area is enclosing the original polygon. So that's one more application of the rotating calipers method. Another one, find the maximum distance between two convex polygons. And how will that work? So you have two polygons, and you have to find a pair of points, one on the first polygon and one on the second polygon, that give you the maximum distance between them. Again, rotating calipers around the two polygons, but now you're rotating them around the two polygons simultaneously, not just one. And as you rotate them against both polygons, you'll find the farthest pair of points of the two polygons. So that problem is solved also by the same technique of rotating calipers. Find the convex hull of two convex polygons. You have two convex polygons, and you'll find a convex hull of each. So you need to find lines of support, lines that go from here to here, so that you get the envelope of the two convex hulls, and then you can eliminate the two inner pieces of the convex hull, just get the outer piece of one convex hull, the outer piece of the other convex hull, plus these two parallel tangent lines that are on both sides tangent to both polygons, and splice them all together, and you get the convex hull of the original pair of polygons together in linear time using this rotating calipers method. So you get one more problem solved out of that, again, in linear time. All these problems are solved in linear time. Intersecting two convex polygons. You can do that with a rotating caliper also. Find the largest pair of parallel lines that separates, by large I mean the largest linear strip that separates two polygons which are not intersecting. This is used a lot in machine learning and other scenarios. You want to find separating, not just a separating line, but a separating strip between two convex polygons. Again, if you think about it, you'll see parallel, the rotating caliper method by parallel rotating a pair of lines will give you the answer to that, largest separating strip. That's what this is. And there's other problems here which I'm not skipping out altogether, but the optimal strip separation and optimal line separations, and lots and lots of problems which are used, which use the rotating calipers method to solve. Okay. Visibility problems, there's computer vision problems that are solved by this. Triangulations, if you want to find a good triangulation between two polygons, one of which is contained in the other, triangulation means you take a polygon and you slice it into triangles. That's what triangulation means. Create a bunch of triangles in there, only using the vertices of the original polygons. And triangulations are used a lot in computer graphics and lots of different applications, modeling and simulations of various kinds, virtual worlds. They all use triangulations. So anyway, there's about 15 different problems in this paper alone that rotating calipers solve, and all in linear time, which is a big win, because linear time is a lower bound for all of these problems as well. Obviously, you have to look at every point in the input. Very straightforward lower bound argument. So rotating calipers, in summary, gives you optimal algorithms to solve dozens of different problems. Optimal algorithms, all linear time. So you get a lot of mileage out of this technique. It's very robust. It's very general. You can use it in many different scenarios. Any questions about any of that? Okay. So a few more facts about point set diameters. So the diameter of a point set, the farthest pair of points, because up to now we just did the diameter of a convex polygon. But what about the diameter of a point set? The farthest pair of points in just an arbitrary set of points, not a polygon, a point set. Well, it turns out that you can show pretty straightforwardly that the diameter of a point set, the farthest pair of points, is equal to the diameter of its convex hull. How many believe that? You can see it kind of intuitively. I mean, it requires proof, but the proof is pretty straightforward. Okay, so with this theorem in hand, we can say, okay, now we can use that rotating caliper method to solve the diameter of not just a polygon, but an arbitrary point set. How? First compute the convex hull, and then do the rotating calipers around the convex hull, and in linear time you can find the diameter of the point set once you have the convex hull. But first you have to compute the convex hull, and how do you compute the convex hull? Well, we already saw a lot of algorithms for that. Gram scan, Jarvis's march, merge hull, quick hull, lots of others, Chan's algorithm. So that's how you can handle point sets. So also finding the diameter of a point set requires n log n time. That you can't do in linear time, it turns out. That theorem is a lower bound. It's not easy to prove, but it's true. So n log n time is required, lower bound, to find the diameter of a point set. Not of a convex polygon. That we can do in linear time, like we just saw a few slides ago with the rotating calipers. So the bottleneck in finding the diameter of a point set is really computing the convex hull, because the lower bound on finding the diameter of a point is already n log n. So if it's already n log n, well, find the convex hull first, because that's how long you're going to have to spend anyway, n log n. So you might as well use gram scan, say, and then use rotating calipers to find the diameter of that convex hull, and then you'd have the diameter of the point set that you started with. So the convex hull becomes a subroutine in finding the diameter of a point set. Now you see how we're starting to use all these computational geometry techniques as building blocks to build more and more sophisticated algorithms from them. So because we can find the diameter of a point set by first computing its convex hull using gram scan, which takes n log n time, and then doing rotating calipers in linear time, that's an optimal algorithm to find the diameter of a point set because of this lower bound technique. Right? So we just proved the optimality of this approach right there. Right? The optimality of what? Of using n log n time to find the diameter of a point set. So first find the convex hull, say using gram scan, and then use rotating calipers on that convex polygon like we did a few slides ago. Okay. But we can do even better than that, because we can use Timothy Chan's algorithm for convex hull that runs in time n log h, not just n log n. Right? So if you use Chan's algorithm, remember how that works? It merges gram scan or Jarvis's march in kind of a divide and conquer kind of approach, fuses them together. So the diameter of a point set can be found in time n log h, not just n log n. And notice that this bound of n log h doesn't break the upper bound of n log n, because h could be as high as n. So then they'll be the same. But if h is lower, it'll run faster. It'll run in time n log h, not n log n. If n is much smaller, if h is much smaller than n, that's a win. And this, another reason why this doesn't break the bound, besides not being general, and the bound is in general, is that this bound is given in terms of not just the input, but in terms of the output h, not just the input n, the input parameter n, the number of points, but the convex hole size h. So it's a bound both in terms of the input and the output. It's an output sensitive bound. And so that's optimal in terms of both parameters right there. So these are two optimal algorithms to find the diameter of a point set based on, say, Graham-Scamm in one of them and Timothy Chan's convex hull algorithm runs in time n log h. And the two, none of these results contradict each other, of course. But just so you know. Any questions about any of this? Yeah. This right here?
The upper.
Right here? Oh, that lower bound we didn't prove, but somebody proved it a long time ago. It's not easy to do. Like the lower bound for sorting, the lower bound for convex hulls. Remember, sorting was kind of information theory kind of argument based on the decision tree, and the log being the log of the factorial being n log n. The lower bound for convex hulls, we squared all the points of a sorting instance, raised into the parabola, and then from the convex hull inferred the sorted order. This argument right here is more complex than either of those. So I'm not gonna present it here. But if you want to look it up for extra credit and tell me what you think and convince me you understood it, I'll give you some credit for that. It's worth it. Any other questions? But regardless of how this is proven, given that this is true, it makes this algorithm optimal because it works in time n log n. All right. So the width of a convex polygon can be found in linear time. We already mentioned that. The diameter of a simple polygon can be found in linear time. By the way, simple polygon means not self-intersecting, but it doesn't have to be convex. It could be like the picture of the Mona Lisa. So how do you find the diameter of an arbitrary simple polygon in linear time? I'll let you think about that. Yeah.
So its diameter is the same as the convex hull of it.
Yeah.
So you can do a grand scan to figure out the convex version of it and then convert it.
Yeah, you can use Gabriel and then use rotating calipers, but you just spend n log n time.
But you already have the points in a simple polygon. I guess they're not necessarily polar angle sorted.
Yeah, they're not necessarily polar angle sorted, but you can just go around and sort of do the Graham scan kind of trick, but you skip the sorting step. That's important. Otherwise, you'd be spending n log n time. Yeah, so it's a modified version of Graham scan, basically, is what he's saying, and he's right. There's another theorem about a lower bound that we won't prove here, but it happens to be true. Again, for extra credit, look it up and explain it to me. But the problem of element uniqueness, I give you a bunch of numbers. I say, are there any two equal numbers in this set? They're not sorted. Now, obviously, you can do it in n log n time. How? Find if the points are all unique. Then I guess the points here are just numbers, one-dimensional numbers. So when I give you n numbers, I say, are they all unique, or is there a duplicate somewhere? At least one or more duplicates. That's the element uniqueness problem. Pretty straightforward. Are there any duplicates in this list of numbers? Yes or no is the answer. How fast can you do it if you're allowed n log n time? How would you do it if you're allowed n log n time? One word. Sort. Yeah, and then go down the sorted list, and you'll find duplicates. They'll be right next to each other, right, in a sorted order. It turns out that there's no faster way to do it than that, because you're not being asked to sort anything. You're being asked to just the yes/no question, the Boolean query of yes/no, is there a duplicate or isn't there? So the answer is just one bit. Sorting has to return an entire list of stuff, so maybe that's why it takes n log n. No, this one takes n log n also, and the answer is just one bit. Are there any duplicates or not? It's not trivial to prove, so we're going to skip the proof here. But it happens to be true. But this result, remember this result, because we'll use this theorem, this result of n log n lower bound on element uniqueness, to prove many other things later on. Many other lower bounds and other interesting things. Okay. So that sorting approach turns out to be optimal right there, is what we're saying, given that this is true, this lower bound is true, n log n. Sort and then look for duplicates are right next to each other in the sorted order with using one big linear scan after the sort. Turns out there's no faster way to do it than that. Okay. I guess let's talk about some Voronoi diagram related issues. Voronoi diagrams are basically, they capture proximity information. So you have a bunch of points in the plane, and by the way, all these concepts, including diameters and everything else, generalize to higher dimensions, and not even just Euclidean spaces, but other kind of metric spaces, and not even non-metric spaces. So you want to compute the set of points closer to a particular designated red point here than to any other blue point in the set. So what would that look like? Basically a convex polygon like that. So this convex polygon basically captures and closes all the points that are closer to the red one than to any of the blues. So any point inside the polygon is closer to the red nucleus here than to any of the blue points outside the polygon. That's the Voronoi cell of that point, of that red point. Okay? And you can compute these Voronoi cells of all the other points. And that's what they look like. So some of those Voronoi cells are unbounded. And by the way, it was invented, this kind of proximity diagram was pioneered, defined, and invented and explored by Dirichlet and Voronoi back in the 1800s, before computers even. And they have a lot of applications, thousands and thousands of different applications, all over mathematics and now all over computer science. So it's called a Voronoi diagram, or a Dirichlet tessellation sometimes, or a Dirichlet diagram. So every point induces a convex cell around it, such that every point in the interior of that cell is closer to that point than to any other point outside that cell. How many understand this concept or definition? Okay, any questions about that? And it turns out these cells are always convex. They're not always bounded. Some of these cells go unbounded off in some infinite direction. Why? Because any point out here is closer to this than to the rest of the points. There's only a finite number of points n. How many can see that some of these cells have to be unbounded? Yeah. And this concept generalizes to arbitrary dimensions. In 3 dimensions, it'll be kind of polytopes, convex polytopes around each point, and it'll be a 3D configuration with still some cells unbounded, pointing in every direction. Okay. And in fact, the picture on the cover of this book is of the Voronoi diagram and its dual, which is a Delaunay triangulation. But it's such a basic concept, the 2 authors of the computational geometry book decided to put it on the cover. It's that important. And it's in chapter 5, specifically in section 5.5, it starts talking about these Voronoi diagrams. How many have started looking at this book, by the way? Really? How many are aware that it's been on the class website from day one? Okay. How many downloaded? Okay, so at least you downloaded it if you haven't looked at it. Okay, I'll give you credit for that. That's good. But open it up and start looking at it. That'll be even better. And try to do it before the midterm. Okay, so you see these pictures I had on my slides come exactly from page 205 of this book. Here's a Voronoi cell. These are the locus of points closer to that point than to any other point. And then each point induces another cell, and it looks like a honeycomb kind of construction. Very general, very applicable to any dimension and even to non-Euclidean spaces. So in 3D, the cells begin to look like this. They're like volumes, they're polytopes. And here's another depiction of these kind of cells in 3D, but it definitely generalizes. It's used in statistics a lot, for example, this kind of concept. Things that are closer to a point are more similar to that point in various ways than similar to other points. Right? So you can get a lot of kind of similarity information. Here is what it looks like in other metrics. So there's something called the LP metric. So LP metric is a generalized metric that looks like this, where P is the exponent of the differences of the x's and the y's, respectively, and you raise it to the 1 over p's power. So for p is equal to 2, what kind of a metric is this for p is equal to 2, where the distance is given by this equation where p is equal to 2? Euclidean metric. How many see that? But p doesn't have to be 2, right? If p is some other, it generalizes to arbitrary dimensions, not just 2 dimensions. So, for example, Euclidean metric, that's L2 because p is equal to 2. So L sub p is L sub 2 and p is 2. You get the Warner diagram, it looks like this. But in another metric, let's say L1, where the Warner diagram is very different now, it's called the Manhattan metric because it's just a difference in x's and a difference in y's. Really raised to the first power and taking the 1 over p power, but p is 1 in the L1 metric, in the Manhattan metric. So you just get delta x plus delta y. No exponents, no square roots. And it's called the Manhattan metric. Why do you think it's called the Manhattan metric after New York? Yeah. Yeah, because the streets in Manhattan are all rectilinear. They're all right angles to one another. So the distance, the walking distance from one point to another point is the distance over on the avenues and the distance over to the streets. How many streets up and how many avenues across? How many get that? And because you can't go diagonally through a block, there's a building there. So that's why it's called the Manhattan metric. And it's a very important metric in VLSI design and in architectural drawings and simulations and all sorts of things. And there's lots of other different metrics. You can plug in any P and you get a different metric. And by the way, the P doesn't even have to be an integer. It could be a real number in general, a fraction or a real number. But this is the exact same point set. Look, the points appear in the exact same positions, x's and y's. But the metric, the distance, is defined differently. And so the Warner diagram looks very different than for the other metric, even though it's the exact same point set. So distances are defined differently in different metrics. Right? And often you want to change metrics or use non-conventional metrics or some esoteric metric for whatever reason. And it works out for that problem domain. And then you can have dynamic Warner diagrams. Warner diagrams that change with time because the points are moving, or new points are being added and old points are being deleted, or in general they're just moving. So here's a simulation of a Warner diagram that changes in real time as the points move. And so you can kind of see the effect of motion on these points. You see some cells are growing, others are shrinking, and the ones on the periphery are always the unbounded ones that go off to infinity. So not all cells are bounded. And some cells kind of swap around as the points move past each other. That was not easy to come up with this simulation. Here's a simulation in 3D. So there's points in there that are moving around, and the three-dimensional cells, like soap bubbles, are kind of varying with time. But that's a 3D analog of the dynamic version of the Warner diagram problem as the points move around. And by the way, this is all in Euclidean metric, not in Manhattan metric or Chebyshev metric, or which is sometimes known as L infinity, which is the max the max of delta x and delta y. That's the L infinity norm, the Chebyshev metric. Just FYI. Any questions about anything so far? Yeah. The polygons will say convex always. Yeah. So you can prove mathematically that the locus of points closer to a given point closer to a given point than to any other point will always form a convex polygon. It wouldn't be non-convex. Why? Because if it looked like this, any points here will be closer to the point than these points are. And they'll have to be also within that polygon. So that polygon, that's the locus of points, will always have to be convex. It's an intuition, it's not a proof, but the proof is not hard to show. That book I showed you has that proof in it. So, reason number 23 and why you should read that book. Because facts like that, what we're just stating here and moving on because there's not enough time, are actually proven in the book. The proof is just a paragraph or 2 paragraphs of mathematical argument, and it's pretty straightforward, but still, it's non-trivial. Any other questions? Yeah, so Voronoi diagrams are so common, so ubiquitous, so useful that there's entire conferences every year about Voronoi diagrams. How many realize that? Well, let me not be presumptuous. How many heard about Voronoi diagrams before today? Okay, that's good. So you heard about it. Well, there's entire conferences on this topic that deal with nothing but Voronoi diagrams, which is amazing. But given how ubiquitous and useful and common and pervasive these Voronoi diagrams are across many fields of engineering and science and math, if you start thinking about it that way, it's not that surprising. And there's multiple conferences on it every year. This is the International Symposium on Voronoi Diagrams in Science and Engineering. And it's all pretty recent versions of these symposia. Right? It's used in modeling and astronomy, bioinformatics, geography. These are just some of the application areas. They're used in operations research, right? Lots of different areas. So in statistics and image processing. So here's a Voronoi diagram of all the capital cities of the 50 states of the United States. So it kind of resembles the map of the United States. Not quite the map of the United States because the United States map is not based on Voronoi diagrams. It's based on geographical and historical accidents, coincidences, but still, that's an interesting depiction of the U.S. And the Voronoi diagram of all U.S. airports look like this. Why is that important? The Voronoi diagrams of all the airports in the U.S. When is that important? This specific diagram. In case of emergency, airborne emergency, how many can see that? Yeah, I mean, the president's computer better have a good grasp of this diagram because, in case of emergency, ideally you should be redirected to the closest airport, not some airport that's far away. So as you fly around between these cells across the United States, you always want to know the closest airport to you, or at least your computer better know, so that in case you need to land in a hurry, you don't have to travel very far. Yeah. Yes, yeah. He's asking, does this kind of diagram or something equivalent influences flight patterns? The answer is absolutely it does. So sometimes planes take a longer route because they're more closer to certain airports in case something goes wrong and they have to do an emergency landing, or there's a situation, or even a terrorist takeover of the plane or whatever, and it needs to land in a hurry or for whatever reasons. Sometimes flight plans take that into account. And there's these big routes in the sky. You don't want to take routes that stay away from major airports, most of the route, and have these distances to the nearest airports be very far away. The closest airport, the entire route is at least 1,000 miles away. That's not a very safe route for a lot of reasons. Unless it's completely unavoidable. Like, if you're flying across the Atlantic and there's no there's no airports because there's no land masses, still you want to minimize the airborne time far away from airports once you get close to land. Or you fly several planes together across a few miles apart, and they can keep an eye on each other. If one of them gets into trouble, the other pilot can immediately report and maybe hover around or until help arrives or something. Or you try to fly over places that has cruise ships close by below you. Cruise ships have these routes also. So you can kind of pair up planes with cruise ships. In case a plane goes down, there's a cruise ship 10 miles away that can come and throw the lifeboats in the ocean and save people and not let them freeze like that movie Titanic, hopefully. Anyway, but and on the fun stuff, on the more fun side, there's Voronoi furniture, like Voronoi shelves and Voronoi chairs, and so the Voronoi motif, is actually used in architecture and in design and in furniture and in art all over the place. There's some Voronoi tables. So if you see one of these one day, and you've probably seen them already, you just didn't know what they were. It has this kind of very pleasant kind of aesthetic about it. There's a Voronoi shoe right there. I'm not saying it'll be the most comfortable shoe, but still, now you know what you're looking at when you see Voronoi architecture. That's a Voronoi staircase, a Voronoi screen door. You actually see these in real life. And it has kind of a nice aesthetic to it because these are convex cells and they have this mathematical definition of any point inside them is closer to the seed of that cell than to any other point outside. Right? There's another Voronoi building, Voronoi facades. It's pretty pervasive when you start noticing it actually in real life. Even nature has Voronoi diagrams. If you ever see a giraffe, now you know. The giraffe skin has kind of Voronoi patterns. So there's a turtle shell. A honeycomb is actually a Voronoi diagram. It's just very regular. All the points are spaced apart in a grid, and then it gives rise to hexagons. And they're all the same. But Voronoi diagram, honeycombs are Voronoi diagram. And even macroscopic things like land masses create Voronoi diagram kind of shapes, insect wings. It's very pervasive. You can even have Voronoi art. So if you're doing a TSP kind of TSP art, right? Remember we saw the Mona Lisa as one giant closed simple curve. How many are doing this kind of project for the class? Nobody? A few people? That's okay. It's good. You may want to consider it. You can throw in some Voronoi kind of spin on it as well, not just TSP and not just MST, minimum spanning trees, but create some Voronoi art. So there's another idea for the term project for you. So for example, you take a picture and you make this kind of Voronoi kind of art out of it. So it could be kind of tessellated like that, almost like a mosaic kind of an effect. So I'm just showing you a few examples of Voronoi art. There's the Voronoi Mona Lisa. We already saw the TSP, Traveling Salesman Tour, Mona Lisa earlier. It's a famous Japanese drawing, kind of made into Voronoi format. There's a Voronoi cat. Any question about any of that? So that's a term project idea right there. It'll look pretty neat. All right, so back to the mathematical side. So a Voronoi cell is unbounded if and only if the point associated with it is a convex whole point. You can prove that. The book that I showed you, Barata and Shama's textbook, it proves this theorem. It's not hard to prove. It's a couple of paragraphs of argument. So there's an interesting relationship between the unbounded regions of a Voronoi diagram and the convex hull. Right? These unbounded regions, the points associated with these unbounded regions are the convex hull points, which suggests that if you have the Voronoi diagram, you can get the convex hull for free. Just take the points associated with the unbounded regions, and those are the convex hull points. Right, and here I'm highlighting them in red. These are the convex hull points. So if you have the Voronoi diagram, you can compute the convex hull points from it in linear time, which essentially is for free. Anything you can do in linear time is usually for free, because you have to look at the input anyway, and the input is already linear in size. Right, so there's a convex hull related to the Voronoi diagram. In fact, we're about to see that the Voronoi diagram captures a whole lot of other concepts in computational geometry. Proximity kind of information and farthest distances and closest distances and convex hulls and triangulations and lots of other things. So it's a unifying concept. Ian Shemes, one of the two authors of this textbook by Shemes and Preparata, in his PhD thesis, founded this entire field of computational geometry, and he's the first to show how to compute the Voronoi diagram in n log n time. He didn't define the concept. The concept was defined in the 1800s by Dirichlet and Voronoi themselves, but he's the first person that showed that you can compute it efficiently in n log n time. Before that, we didn't know how to compute it fast, because from it you can compute lots of other things. So he gave a sweeping kind of a grand slam win of lots and lots of algorithms, all in optimal time, based on the fast computation of the Voronoi diagrams as subroutines. That was one of his major contributions. A brilliant piece of work. Every nearest neighbor in the Voronoi diagram defines an edge. Okay. So if you say, what's the nearest neighbor to this point? This point has its nearest neighbor being this guy, so you draw the arrow there. This guy has a nearest neighbor being it, this guy here, so you draw that edge. These two guys have their nearest neighbors being each other, so you draw the two red lines. If you draw red lines for every point to its nearest neighbor, the closest point to it, all those red lines will define Voronoi diagram edges, right? So the Voronoi diagram captures proximity information, closest neighbors. That's not to say that every Voronoi edge represents a closest neighbor. Like this edge here does not represent the closest neighbor, because this guy's closest neighbor is this one. This guy's closest neighbor is that one, and there's no red edge running across this blue edge. So we're not saying that every blue edge is a closest neighbor relationship, but we're saying every closest relationship is a blue Voronoi edge. Okay, so remember which direction this is going in. So if you want to find all nearest neighbors, every point find its nearest neighbors and do the same for all of them, all you need is a Voronoi diagram. Because all you got to look is every blue edge and see which ones correspond to nearest neighbors and which ones don't. And some of them won't, but the ones that do will be the nearest neighbors. And there's only a linear number of blue edges in the Voronoi diagram. In fact, there's a much more general theorem than that. Any planar graph only has a linear number of edges in it. What's a planar graph? It's a graph that can be drawn in the plane without any two edges crossing. It's any tessellation of the plane, like a planar subdivision, or any planar graph in general. Every planar graph has at most roughly 3n edges in it, a linear number of edges. Because graphs in general, graphs being nodes and edges, could have a quadratic number of edges in the number of nodes. Every node could be connected to every other node, and then you have n choose 2 edges. So the number of edges in a graph could be quadratic, but the number of edges in a planar graph is not quadratic, it's linear. And a Voronoi diagram is a planar graph. It's a very special kind of planar graph, specifically. Okay? So Voronoi diagrams yield all the nearest neighbors for free. And if you know all the nearest neighbors, you know the closest pair as well. It's just one of the n pairs of nearest neighbors. Okay? So from the Voronoi diagram, you can compute a lot of other things for free. Okay? And it doesn't stop there. It keeps going. Right? So again, this is what I said a minute ago. A Voronoi diagram is a planar graph, and so the number of edges is linear. In particular, it's at most 3n minus 6. You can show that planar graphs have no more edges than 3 times the number of vertices, minus 6. Okay. So you can do nearest neighbor search in logarithmic time if you have a Voronoi diagram kind of structure. How? Planar subdivision. Remember the planar subdivision search? Where you have arbitrary polygonal planar subdivision? How many remember that from like 3 or 4 lectures ago? Don't tell me it's nobody. We spent a good time on it. You have an arbitrary polygonal planar subdivision, a lot of partition of a plane into a lot of polygons. Not necessarily simple, not necessarily convex. Right? And then you partition it into these polygons, and for a given point, you want to ask which region of the partition is that point in. So you want to do fast queries in logarithmic time. Remember, we did the slab method. We divided it into strips, And each strip, you had all these trapezoids, and you did a pair of binary searches, and that tells you which region any given query point falls into. The region, the subdivision is fixed. The query points vary. They change over time. The new query points come along. But in a pair of binary searches, you can locate a point inside a large planar subdivision. How many remember it now? I kind of described how. Oh, good. I picked up another 10 people. The rest of you, okay. Well, I guess look it up. So a Voronoi diagram is a planar subdivision, and you can do this trapezoidal method on this diagram, right? Which means in logarithmic time you can do a nearest neighbor search for arbitrary points. For any query point that falls into this diagram, like here, it'll say, oh, that's the nearest point. If I put the point here, it'll say, oh, that's the nearest point in logarithmic time, using this planar subdivision and a lot of pre-processing and partitioning into strips and then trapezoids and all that stuff that we did a few lectures ago. You can apply it to this scenario. And you can do very fast point location, right? And it's important that it be fast because you can have millions of queries a second coming at you, given a fast, kind of computing scenario, but the orientation and the positions of the points is fixed. These are like airports on the ground. And you want to find, for people traveling or flying or whatever, what's the closest airport to me? Okay, and that you can do very fast. Yeah.
So we've talked kind of about unbounded polygons.
Yeah.
And I'm not really sure what the best way to store that information would be.
Oh, okay. He's asking a practical question. How do you store these unbounded polygons? I mean, you definitely don't want to take infinite storage to sort of go off to infinity to designate an unbounded. So how would you store it as, unbounded polygon? Fair question. Well, I mean, there's lots of ways you could do this, but name 7. All right, name just 3. The point is, it's more than one, right? How would you store this unbounded polygon in some disciplined way so that your algorithms recognize it as such, an unbounded polygon? Yeah. Yeah, you can store it as, most simply, you could probably store all the edges. You can store this edge, and then this edge, and then this edge, and then that edge. And how do you store an edge that's really array? It starts here and goes off to infinity. Well, you store one point and the other point. It's direction. It's stored as a vector. It's a vector starting here, pointing in that direction, arbitrarily far. So it's not a two-pointed segment with 2 points being the endpoints of the segment. It's just a vector at this point in this angle. And the other edges, just store them as pairs of points, 2 endpoints of the. Another way of storing it, like what he was alluding to, you can store that polygon as a bunch of half spaces, bunch of half planes. So take this half plane here and say everything above this half plane, everything above this half plane, everything above this half plane. Above, I mean on one side and not the other side of the half plane. And then everything to this side of that half plane. And it's the intersection of all these half planes is this unbounded polygon. Implicitly, you say it's the intersection of the following list of half planes. How do you define a half plane? Linear inequality. Right? How many get that? So a bunch of linear inequalities will get you that too. But that's a little more implicit, because to actually find a polygon, you need to then compute the intersection of the half planes, which can be done quickly, by the way, but it's a process. You're probably better off just storing the segments and or vectors for the unbounded segments. And there's lots of other ways to do it. But we just named two ways of storing it inside a program, say. All right, so with planar subdivision search, you can find quickly points which region a point falls in for a created point. And here I'm showing you the animation from a few lectures ago that we just talked about, just to refresh your memory, right? Form these slabs or vertical strips, and using these vertical strips, partition each into trapezoids, and these trapezoids fill the strips, and using a binary search in the vertical direction, and first a binary search in the horizontal direction, find which strip, and then which strip, which trapezoid, and so that's the beauty of these subroutines. Now we can use them in larger and larger, more complex methods and algorithms to do bigger things. Any question about any of that? All right, so if you start to connect points that lie on neighboring cells of these Voronoi diagrams, so basically if you connect this point to this point, and then this point also to that point, but don't connect this point to that point because these are not neighbors. Their cells don't touch each other. So only connect points whose Voronoi cells touch each other, are neighbors. Once you start doing that, you get a triangulation. And it's not just any triangulation, it's called a Delanoë triangulation. And that was invented by Boris Delanoë in the early 1900s. And it's called the dual of the Voronoi diagram sometimes because you replace these edges with other edges that cross these edges. The red edges cross the blue edges. They connect points whose blue Voronoi cells are touching each other, are neighbors. And this triangulation is very interesting because it has really cool properties. It maximizes the minimum angle of any triangle over all triangulations, it turns out. Because when you want to compute first of all, computing triangulations is not easy. It takes a while to compute them. And the Voronoi diagram gives you them for free. For free, I mean linear time, assuming you have the Voronoi diagram on your hands. And why do you want triangulations to begin with? What's the use of a triangulation? Well, in finite element analysis, in modeling, in simulation, in lots of other areas, in our architecture, in computer-aided design, you need triangulations to create a simulation of a non-polygonal object, but using polygons to approximate it. Okay, so even in graphics, when you have a little bunny, in a video game or virtual reality simulation or some sort of a movie animation sequence, you have a bunny. It's not really a bunny. It's about 100 million polygons. How many know that or have seen that or heard about it? So everything is made of polygons in computer graphics and simulations and animation. It's just so many polygons and they're so small that it looks like a continuous curvy object, like a fluffy little animal. But it's really a bunch of polygons strung together. So you often need to triangulate objects in order to approximate them and make them discrete. Like when you simulate an airfoil, a wing in a virtual wind tunnel, not a real wind tunnel, but a virtual one, because it's a lot cheaper to simulate it in silico rather than in reality. You need to convert the wing into a bunch of polygonal, objects that simulate the overall curvature of the wing, and you don't want very long slivery triangles. You want kind of short, stubby ones, right? Because the simulation involves locality. Things only interact with things that are close to them, not with things that are far apart. There's a principle of locality to the universe. Quantum mechanics being an odd exception to that, based on entanglement. But never mind that. Usually it's locality that rules the universe. Things here only interact with things that are close to them. And if they're going to interact with things that are far away, they first have to interact through a series of proximity interactions until it gets far out, but not directly. Okay, so you want triangulations which have small, stubby triangles rather than long, slivery ones. And the linear triangulation is the winner of all these possible triangulations. The triangulation is not unique. There's usually an exponential number of possible different triangulations for a fixed point set. The linear triangulation maximizes the minimum angle of any triangle over all such triangulations. Amazingly enough, that's not easy to prove, but it's true. So that's what this says here. That's a theorem. And in the book, it actually proves that. So again, if you want a triangulation, not just any triangulation, this gives you, the Voronoi diagram gives you a very nice triangulation for free. By again, free we mean linear time. And you can compute a minimum spanning tree from it for free also. Okay, so it turns out that a minimum spanning tree is a subset of the Delaunay triangulation, always. What's a minimum spanning tree? It's a tree that spans all the points that has least total weight. By weight, we mean the sum of the lengths of all the edges. So it turns out that this red Delaunay triangulation always contains a minimum spanning tree inside. And because it's a planar graph, it's only a linear number of edges, it really greatly reduces the total number of edges that you have to consider when computing a minimum spanning tree, which means now you can compute minimum spanning trees very quickly if you have the Voronoi diagram first. So you see the Voronoi diagram unifies and ties together all these other seemingly separate problems and gives you a lot of different solutions to a lot of different problems for free, assuming you had it to begin with. And that's one of many reasons we study these things, right? So all these problems, nearest neighbors, closest pair, triangulations, Euclidean minimum spanning trees, they're all doable in n log n time given the Voronoi diagram. Actually, so the Voronoi diagram is really the bottleneck in many other algorithms and subroutines to solve many other problems, right? Now it turns out that there's a lower bound of n log n on all of them. So all of them can be done in n log n time. Okay? And there's an n log n lower bound required for all these problems and many others. I'm just showing you like five like archetypical problems that the Voronoi diagram kind of unifies and ties together. So basically the Voronoi diagram could be used to solve all these problems in n log n time, right? And assuming you can solve the Voronoi diagram in n log n time. And that's the big if, that's the big trick to do that. Okay, so basically it means all these algorithms are optimal right there. Wait for it, yeah, there we go. So n log n bound on the low side, lower bound for all these problems, and given the Voronoi diagram, they could all be solved in n log n time as well. All this is explained in the book. Again, so I'm kind of superposing my pictures of Voronoi diagrams and the line triangulation on the cover of this book, which now you see even more why this is appearing on the cover. It's a greatly unifying subject and construction and technique that's used to unify many other things, besides what we just saw. Any questions about any of this? Okay, so next time we'll go deeper into Voronoi diagrams and these relationships, and we'll show some lower bounds on these problems. So, because right now we just gave the results. Next time we'll go deeper and show the actual proofs on some of these and more further techniques. I posted on the class website or emailed to you this morning the midterm dates, which is the last 5 days of the month, what we talked about last time. Any questions about the midterm? People ask me about the project. The project is due before you take the final. So it's due like right after the end of the last lecture. So I want you to give a demo of your project. The TAs will, you'll demo it to the TAs. You can work in groups of 2. So you can either work by yourself or you can work with a partner. In rare cases, I would allow a group of 3, but I will not allow a group of 17 people. Obviously, it's just not going to happen. Any questions about the project? Something demoable, something interesting. Doesn't have to be anything in particular. We already gave us some ideas of projects, TSP and Voronoi Art and lots of other stuff. Just don't do Sudoku. Don't do that. That's just boring and way overdone and pretty straightforward and obvious. So. All right, so we'll see you next time.
So just making sure this is not getting recorded.
Yeah, let me...